Hey everybody, and welcome back to another fun and exciting pre-calculus class. Today we're going to continue in chapter number 16, 16.2. We'll be talking about the first derivative. Now, this is like real calculus stuff right here, right? These are words that you've never heard before. So you're like, whoa, cool. Okay, well, it took us all the way through the book to get to this last chapter, but this is kind of the payoff. This is where we've really gotten through the pre-calculus part of it, and now we're finally into real calculus. What are we learning here today with the first derivative? Go ahead and look down in your books. We are on page number 310, page 310. So the first derivative, if you remember in the last lesson, I kind of hinted toward this. I showed you these slopes, these what's called tangents. Okay, so at different points on the line, there will be different points of tangency. So depending on where on the curve it is, you're going to have a different tangent line. So let's go ahead and go over here and let's look at this. This is Desmos. I love Desmos. It's a great resource for you. You should know how to use it by now. If you don't, make sure that you get on there and you do some different things with it and try to figure it out. Well, check out this point of tangency right here. The point of tangency, and as I move this slider around, my point of tangency moves around as well. I can get it to be horizontal. This right here would be called the vertex of the parabola, right? So when your slope is at 0, say horizontal, you're at the vertex of your parabola. Now, if the parabola is facing up and down. If it's facing left and right, then you'd be at vertical when you're at the vertex of the parabola. So as I move the slider around, you can see that my slope is changing. And down here, this is my slope right here. So I have a 1.2 slope. Can go all the way up to a 2 slope. Now over here, it's negative. So there's a negative 2.6, and I could keep going with that, and this thing is way bigger. The parabola basically just keeps going into infinity, so I can keep moving this up. Now there will come a point at which I can't go any further because I can't get to vertical on this because it's a parabola. That's what's called an asymptote, right? There's going to be a point at which I can't get that slope to be undefined. I can't get that slope to be 0 because the parabola is still going up. So just some things to kind of think about there as we're working through this. I just wanted you to see that. Hopefully that gives you just a little bit more of a visual of what the tangent is. Now, here's what we're going to be doing. Go ahead and turn the page over. Now, let's consider finding the slope of the tangent line. So let's think about this. As that slider moves, as we move that thing across that parabola or the circle or whatever line, the sine wave, whatever we're moving it along, it's going to keep changing, right? So we need to have kind of an idea or a concept of what is changing, what's happening. So what they've done is they've used the Greek letter delta. All right, so the delta right here, this delta x means the change in x. So delta means change. So when you see that in math, when you see this little symbol right here, that means change. Think about Delta Airlines, right? Delta Airlines uses this triangle, so maybe that will help you. The m tangent, or the slope of the tangent, m is slope, okay? So slope of the tangent is equal to what's called the first derivative. That's what we're learning about in today's lesson. So the first derivative is also called the instantaneous rate of change. So the first derivative is where that thing is moving, or where that slope is sliding to based on some what we call parameters. Parameters or limits. If you remember from the last lesson, we have to put some limits on this thing. So let's move back over here to the book, and let me show you this right here. So these would be called the limits. So wherever the A point is, okay, so we just randomly, and it's not random, it's wherever the problem tells you it is, or it's wherever, whatever math problem that you're working on, if it's like a science problem or if it's an actual application, it will tell you what the limit is. So in this case, our limit is right here. This is what's called our first function. Okay, this is function number 1 right here. So this is like the first spot that we start. Where we end, we have our second function. Now, I'm not going to take the time to go all the way through this. I'm just not. But this connects to the limits of what we talked about in the last lesson, and this connects our limits to what we're doing in this lesson. So what we need to find is the limit from the change in x heading toward 0. Okay? Now, if we take the first function, the function of x sub 1, plus the delta of x. What's the delta of x? The delta of x is our change in x. So let's say that this is a 1 and this is a 2. Our change in x would be 1 in that case. What if this was a 1 and this was a 3? Well, our change in x would be 2 because we're going from 1 to 3. So whatever your change in x is, this is the x-axis, right? And let me get that out from behind my picture. So the x-axis right here. So the change in this x, that is our delta x. So we put this, so basically the first function right here plus the change in x minus the function of x1. Now that is what's called the limit, or the first derivative, or the instantaneous rate of change. Several different ways to actually say this, but it means the same thing. All right, now they go through this, and I am not going to take the time to work this big, long problem every time, because that's not how we do it. Nobody does it like this, okay? So they're just showing you this as a way, like, this is how you derive the formula, if you will. So this is how you would find it if you didn't know what the formula was. Let's go to the next page. In just a second, I'm going to talk about this. I'm going to talk about functional notation. But for right now, skip down here and look. The short method to find the derivative. Why is there a short method and a long method? Well, the long method is doing it literally the long way. The short method is saying, okay, from the long method, we figured out that there's a faster way to do this. There's a shortcut that we can take. We're going to learn the shortcut, okay? If you want to go back and learn the long way, make yourself happy and enjoy that, okay? But I'm not going to take the time to do it. I'm just not. So let's go back over here to the computer and let's talk about this functional notation first, because it's really important that we understand this. All right, so the function of x is the function you start with, okay? We've dealt with functions. Now, notice this little marking right here. It's like a little quotation mark. That means function prime. That's what that little mark means, and you've heard me say that throughout this year. So the function prime of x is the first derivative, and it's read function prime of x. Okay. Now, this is just notation. I'm not telling you how to do it yet. I'm just telling you how to read it when you see it. Now, do you remember in the last lesson, I told you that there was 2 people figuring out calculus at the same time. There was Newton in England, and there was Leibniz in Germany. Well, the Leibniz notation, it looks a little bit different, but it's the same thing. So this is kind of the Newton notation. This is kind of what they used in England. And this is kind of what they used in Germany and different parts of Europe. It's the same thing, it's just writing it a little bit differently. So with the Leibniz notation, they just use y instead of the function. Okay, so they don't write function of x, they just leave it y. And some of you are like, yeah, why can't we just leave it y? Well, you can with Leibniz notation, it's fine. You don't have to change it over to function. It does get a little bit more confusing the deeper you go into calculus, I think. That's just my opinion. So what you would say if you're looking for the first derivative in kind of Newton's, it's not called Newton notation, but in Newton's way of doing it, in the English way of doing it, f prime of x. And then in this Leibniz notation, we have dy over dx. Okay, dy over dx. The d is actually like change, okay, so this is slope, so the dy is the change in y over the change in x. So rise over run, right? Your up is your rise and run, and your left and right's your run. You remember that? Okay, so this is basically saying the same thing, except for we're just writing it a different way. So it's still slope, okay? And it is the first derivative, and it's read like this. It's read dy dx, just dy dx. You don't say over, you don't say dy over dx every time. You say dy dx, and I think it just is for speed when you're reading it. Or you could also call this y prime. Okay, I have heard that before, but it's not super common. Dy dx is typically what they say if they're dealing in Leibniz notation. All right, one more thing here before we kind of move on to starting to solve these is that, so your m, or your slope, equals function prime of x, or f prime of x, which also equals dy dx. All these things are the same. There's no difference in any of these. It's just writing it a different way. Okay. Now, let's talk about how do we solve these things. So what's the shortcut method that we can learn? So there's two steps to our shortcut method. Step number one, we want to multiply the coefficient by the exponent. And then number two, we want to reduce the exponent by 1. And then there's this little note down here that's very, very important, and the derivative of a lone constant is always 0. All right, so these things right here, very, very important. Just follow your steps and always plug in a 0 for a constant. If you get a constant, plug in a 0. That's all you need to do. All right, so let's go ahead and try this. Let's just follow these rules. So here's our function, and what we want to do is we want to solve this and get our function prime of x equals something. That's what we're looking for. All right, so how are we going to accomplish that? We're going to follow the rules. We're just going to go up here to the rules. This is the short method. So multiply the coefficient by the exponent. All right, now here's another thing. You got to take each one of these separate, right? So these are two separate things. So we'll start with the 6x. So with the 6x, we're going to go ahead and we're going to follow this. And so the exponent is 1. So 6 times 1 is still 6. So how do we deal with this x right here? It says reduce the exponent by 1. So we would have 6x to the 1 minus 1. Okay, well, what is that? This would be 6x to the 0 power, or what is x to the 0 power? 6 times 1, anything to the 0 power is 1, and then 6 times 1 is 6. You don't have to go through that process every time, but I wanted you to see it the first time. Anytime you have a variable to a 1 exponent, in other words, you don't have an exponent, so you just have the variable, that variable is just going to go away. That's all that happens to the variable. So the constant zeroes out. The variable, if it doesn't have an exponent, always just goes to 1. 1 times anything is identity, so the variable just goes away. So here's what we would have. We would have, and then on this one, we know that it's just plus 0. So you don't have to write anything. So our function prime of x is going to just be 6. In other words, our slope is 6. All right, in the next problem in your book, so this is on page 313, they want you to find the slope of the lines tangent to the following function. And then they give you some x values to plug in. So the first thing we need to do is we need to find the f prime function. That's the first thing we need to do. So we need to take this right here and we need to apply our rules to it. So let's go back up and look at our rules. Number one, we need to multiply the coefficient by the exponent, and then we need to reduce it by 1. So let's just go through that with this one here. So we'll do the 4x squared first. So 4x squared is going to be, remember, you take the 2 times the 4, and that's going to be 8x, and then we're going to have 2 minus 1, because we reduce it by 1. So that's to the first, or just 8x. And then we get plus, and then we do the same thing to this guy right here. So its exponent is 1, multiply it by that, and you still get a 2. Remember what I said with any variable that doesn't have an exponent, it just goes away. So it's plus 2, and then anytime that we have just a constant, it goes to 0, so this would be plus 0. We don't need to write that though, so this is our function prime of x, 8x plus 2. Okay, now here's what we want to do. We want to take these x values and plug into that. So we're going to come up with like 5 different answers to this, all based on these 5 different values that we put in. So let's say that we'll create, so -2 equals, -1 equals, and I'll just kind of create a little chart over here, 0 equals, 1 equals, and 2 equals. So what we'll do is I'll go through that, and we'll go through each one of those, and then we're going to get a value that we can fill in over here on this side. All right, so the first one is our -2. So we want to fill in -2 anywhere that you see an x. So now we have the function prime of -2 is equal to 8 times -2 plus 2. 8 times -2 is going to be -16 plus 2 is -14. So in this case, -2 yields -14 as an answer. All right, let's go back and do the next one. So the next one, we're going to just kind of work through it the same way that we just did, except now with -1 going in there. So now we have the function prime of -1 equals 8 times -1 plus 2. 8 times -1 is going to give us -8 plus 2. -8 plus 2 is -6. So 1 would be -6. I'm just going to kind of go back, and I'm just going to take this out, and we're going to plug in 0 in this case. 0 goes there, and then we get 0 plus 2 is 2, so that one is 2. And I'll just go ahead and put in number 1 now. And we get 8 plus 2 is 10, so 1 is going to give us 10. And then the last one there is for the number 2. So let's go ahead and plug in the number 2, and we get 16 plus 2 is 18. And then so 18 would be the fifth one. So all they're asking you to do there is just kind of just plug in stuff, but the first thing that you need to do is you need to find the derivative before you can plug in. So don't forget, this is called the first derivative, okay? Later on in a couple lessons, we're going to learn the second derivative, but this is the first derivative. Now, when do you use that? You use it when you're looking for the slope of the line. And so the tangent slope equals the derivative equals the change in y over the change in x. So all those things kind of coming together there. You know, maybe you were like, I thought calculus was going to be a little bit harder than that. It's not too bad if you really kind of understand the concepts, and then you can plug it all together. Now, it does get harder, but you're learning the base concepts of calculus. So, you know, keep working hard there, keep doing your best to figure it out, and just work through, follow the steps. There's only 2 little easy steps, right? So do those 2 steps, and you should be able to figure out these derivatives. That's all I've got for you. Hope you learned something in this lesson. If you missed anything, slide it back, watch it again. We'll see you later. Have a good one. Bye-bye.